For this week's lab, we had to construct a bottle rocket that could launch as high as possible, then present an estimation or measurement of this height. Each group was provided with 3 unopened 1.25-liter plastic soda bottles, cardboard, a roll of packing tape, and a pair of scissors. According to Newton's third law of motion, an equal and opposite force must act on an object. In the case of linear momentum being demonstrated by the rocket bottle, the only masses evident is the rocket bottle fuselage and the water load inside it. As the pressurized air inside the rocket pushes the water outwards to create thrust through the bottle nozzle, an impulse momentum change is exerted by the rocket bottle fuselage. As the rocket takes off, the only momentums acting on each other is the downward force of water and the equal upward force of the rest of the rocket. The conservation of momentum states that momentum never changes in an isolated system of objects acting on each other, and hence the total momentum of a system remains constant. Momentum is equal to the mass of an object multiplied by its velocity, and it's equivalent to the force required to bring the object to a stop in a unit length of time. This means that momentum is a vector, as it involves both magnitude and direction of motion, so that the momenta of objects traveling in opposite directions cancel out to the sum of 0. Before launch, the total momentum of a rocket and its fuel is 0. During launch, the downward momentum is caused by the expanded air pressure inside the rocket until it is only able to escape from one end. This exerts the equal amount of magnitude to the upward momentum of the rising rocket and creates thrust. The total momentum of the system remains constant at 0. My group decided to cut out 3 triangles of the same shape from the cardboard and attach them around the base of the bottle at approximately 120 degrees from each fin. Prior to our first launch, we opened the bottle and poured out 2/3 of the water, so that approximately 400 milliliters or 400 grams remained as the load within the rocket. Each bottle rocket was then placed facing downwards on a launch stand so that the nozzle end was connected via a pipe to a bike pump in order to pressurize the bottle with air. The first launch we did was pressurized to 40 psi or 40 pounds per square inch and flew sideways after surpassing the tip of the rocket stand. In the second launch test, we decided to attach a nose cone to the tip of the rocket in order to disperse air away from the large surface area to around the fuselage of the rocket. This would enable the rocket to penetrate a higher height before succumbing to the vertical force of gravity. We also attached 4 fins around the cone with the intention that air would disperse easily around the top of the rocket and away from the base, reducing the drag. However, this seemed to only increase the overall drag, causing the rocket to spin uncontrollably at the base as there was no longer any stability from the fins. We were able to accommodate more mass at the top by filling it with water. This was planned to add additional mass that would carry the momentum of the rocket further upwards. This, however, did not work for 2 reasons. Firstly, the water is a liquid that easily moves and changes the center of mass of the rocket, and secondly, the water that was released from the rocket prior to launch was to the ratio of water added to the nose. This meant that the total mass of the rocket remained at approximately 1.25 kilograms, whilst the space for pressurized air was of volume approximately 250 grams. This failed as the mass was too overwhelming compared to the initial impulse of momentum and energy being released. For the final launch, our group observed other groups had built similar models to ours, however they were filling the nose of the rocket with gravel and small pebbles with less water. My group adopted this idea as having a solid mass in the nose would prevent the drastic change in center of mass, and less water in the fuselage would increase initial velocity as less mass is needed to be carried. Additionally, the decision to increase from 30 psi to 40 psi was made to increase the pressure and reduce the overall mass as quick as possible. To estimate the maximum altitude of the bottle rocket, I used the change in velocity formula and the displacement formula, where displacement would be the height of the rocket. This eliminates the issue of calculating changing mass to approximate the consistently changing velocity of the rocket. To find the time at which the rocket was at its peak altitude, I used the View Analysis app to determine the total flight time, which equals 3.9 seconds, then divide this by 2, which equals 1.95 seconds. The change in initial velocity was found by rearranging the formula final velocity equals initial velocity plus acceleration multiplied by time. The final velocity at the rocket's peak would be 0 meters per second, as it is temporarily stationary. The formula can then be rearranged to solve for the initial velocity, where acceleration is gravity at negative 9.8 meters per second squared, multiplied by the time at which the rocket is at its peak, which is 1.95 seconds. This equals negative 19.11 meters per second. Multiply both sides of the equation by negative 1 makes the value positive. Then using the displacement formula, which is the average velocity multiplied by time, the displacement is used as the height. At the peak of the height, the average velocity, which is final velocity, 19.11 meters per second, plus initial velocity being 0 meters per second, divided by 2 multiplied by time, which is 1.95 seconds, equals to the displacement, which is 18.63225 meters, or 18.6 meters to 1 decimal place. The margin of error is hard to quantify as the calculation is only an estimate and the observation of flight was through a moving camera, rather than a stable tripod setup. It is worth mentioning that although air resistance is negligible, the wind conditions during the period of launching, according to the Bureau of Meteorology, was 28 km per hour in the northwesterly direction, hence causing the rocket to rotate on its vertical axis and land approximately 10 meters offline from its origin. The lack of a protractor also limited the exact placement of fins on the rocket to be evenly spaced apart. Also, due to the projectile being a rocket, the momentum is dramatically changing as a result of reducing mass as water is expelled over time.